Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X published on November 25th, 2025, just 2 days ago. It shows that a standard text-to-image diffusion model, trained only for pictures, can be turned into a surprisingly strong zero-shot video object tracker by reusing its self-attention maps to propagate segmentation masks through time and reaching state-of-the-art results on standard video object segmentation benchmarks. The paper is titled, Image Diffusion Models Exhibit Emergent Temporal Propagation in Videos. And as we will see later, the implications for video understanding and tracking are quite significant. Alright, Figure 1 shows how a diffusion model turns a rough text-based hint into a precise object mask. The original image contains a cat and a Christmas tree, and the coarse map only highlights a vague, bright blob where the cat roughly is. The self-attention affinity map then captures which pixels belong together semantically, so activation spread over the whole cat. This propagation step produces a refined mask that closely traces the cat silhouette, which nearly matches the ground truth segmentation. Well, Figure 2 moves from single-frame refinement to cross-frame matching. The input camel frames show a blue point that should track the same spot over time. Cosine similarity spreads that point across many unrelated regions, because raw features mix semantics with generation details. The aggregated self-attention map instead locks onto the correct camel region, giving a tight response. Per head self-attention maps each light up different but still relevant parts, which together create a robust propagation signal. So, while Figure 2 showed how self-attention gives cleaner cross-frame matches than raw features, Figure 3 quantifies that gap over an entire video. The blue self-attention curve stays high, around 70 to 80 in the combined J and FM score, so segmentation quality degrades only slowly with frame index. The orange cosine similarity curve hovers near 30 to 40, and the inset masks show why, because cosine similarity produces blurry, scattered blobs, while self-attention yields sharp, well-localized objects. Alright, while Figure 3 highlighted how good the propagation kernel is on its own, Table 1 shows that the choice of text prompt still matters a lot. The null, class name, and caption prompts all sit around 72 in combined J and FM, so semantic text alone barely helps. Learned prompts, optimized by textual inversion for each object, jump to about 75 J and FM, with both region and boundary scores improving noticeably. So, while Table 1 focused on prompt design, Table 3 compares the full tracking system against prior methods. The table shows that the diffusion-only version of Drift already beats earlier zero-shot label propagation approaches like STC, DIFT, and Dino across all reported datasets. With Segment Anything added, Drift climbs even higher and surpasses SegGPT, SAMPT, and Matcher, despite those models using segmentation training. The final block lists fully supervised video methods, which still leads slightly, but the gap is surprisingly small given that Drift never sees video labels. So while Table 3 compared scores against prior trackers, Figure 8 walks through how Drift actually works on a pair of video frames. The top block shows the previous masked frame and the current target frame being encoded, then run through DDIM inversion with a learned text embedding so the diffusion model produces stable, object-focused attention. Those multi-head attention maps are aggregated into a single cross-frame affinity, which propagates the mask forward. The lower block then normalizes this soft mask and refines its boundaries with Segment Anything, outputting a sharp segmentation in the target frame. So the big takeaway is that a frozen text-to-image diffusion model already holds rich temporal cues, and its self-attention alone can drive strong zero-shot video object tracking. More broadly, this suggests image generative models may be powerful foundations for video understanding. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.